Hello and welcome to this introductory video on inductance. You might at this stage be asking yourself, how is this an introduction to inductance when we've already talked about induced EMFs and things like that because of changing magnetic fluxes? And indeed, we have a conceptual understanding for this, but we have yet to introduce what we really mean by inductance as a physical quantity. So, we've talked a lot about, for example, in the case of our transformer, one changing magnetic field causing an EMF in some other coil that's experiencing that, that is sitting in that field or some way, shape, or form exposed to that changing magnetic field. That is a case of an interplay between, say, two coils. One of the easiest ways to create a magnetic field, for example, in the transformer case, was to have our primary coil that was changing its magnetic field and influencing our secondary coil because its magnetic field, the magnetic field of the primary coil, was passing through that secondary coil. So that is a case of interaction, and we talk about that as a mutual inductance. So our primary coil is changing its magnetic field. As a result, it induces an EMF in the secondary coil. How much of an EMF depended on the properties of those coils, and it depended on both the properties of the primary and the secondary. We saw that in a previous video on transformers, but we'll sum that up by talking about this combined mutual inductance of the two coils. And we know that if we sort of flip the thing around and we use the secondary as our primary and our primary as our secondary, we would expect the same interplay of properties to come into effect. So the reverse would also apply here. One single mutual inductance would talk about what the primary coil does to the secondary and what the secondary does to the primary. Now, what we haven't yet talked about is the fact that if I am sitting there with my primary coil and I forget the core and I forget even the secondary coil in my transformer, I just have one single coil. And I start to try to create a changing magnetic field by changing the current through the coil, then yes, I succeed. I create a changing magnetic field. Or is that magnetic field, where is it? It's inside that first coil, which means there is a changing magnetic flux in the first coil just due to the fact that I'm changing its own current, its own magnetic field. Surely, Lenz's and Faraday's law should still apply. There's a changing magnetic flux through a coil. It must induce an EMF. So this is the interplay of the coil with itself, and so we call that a self-inductance L. And that is, as I've just explained to you, an interplay of the coil with itself. So the change in magnetic flux through the primary coil simply due to the change in the current of the primary coil is creating some inductance, some EMF through that coil that is going to counter or act to counter the change. Okay. Now, the other change in order to introduce this physical quantity of inductance, M and L, is going to be the fact that we want to not so much talk about the flux through, but realize that in each situation what we're really doing is playing around with a current. So we'll talk about the inductances not in terms of d phi dt, but rather di dt. And then we can write down our defining equations. When we are talking about the interplay between two coils, the EMF that the first coil induces in the second one is given as minus the mutual inductance times the time rate of change of our current. Or if we're talking about what's going on in terms of an induced EMF in the coil itself, simply due to its own changing magnetic field, then we're looking at that second expression that the EMF is minus the self-inductance times our time rate of change. Now, looking at that, the units of inductance for both the mutual and self-inductance case are going to be volts times seconds per amp, or simply ohm seconds.